Welcome everybody, welcome to my webinar. My name is Erik Henneken. I will take you through the Tribus group. I'll say a few words about myself, and I'll tell you more about the Movitas, the reason why we chose the Movitas, the concept, some technical details, and about the future of it. So the Tribus group, it was founded 22 years ago by three men experienced in converting minibuses. We are in Utrecht, in the center of the Netherlands, with 3 locations close to each other. Innovation and sustainability have always been part of our DNA. Tribus has 3 divisions actually. We are converting minibuses and we are supplying parts for other dealers and distributors to convert minibuses by themselves. And we have the Movitas, which I will tell you more about it. We are exporting our parts to 19 countries and counting. And last year we converted some 1,800 minibuses, which makes us a market leader in the Netherlands, and we are expanding more and more to other countries. So about me, I have been involved in mobility, automotive mobility for the past 30 years or so, mostly in commercial innovative roles, and since 2017 working for Tribus. So what made us get into this segment of minibuses? Well, you see this picture here. It's a city in Asia somewhere, and you can almost not see the city because of the fumes, the emissions. You can imagine the noise it generates. It makes cities very hazardous to live in, and that is one of the reasons we decided to start developing the Movitas, but I will tell you a little bit more about it, because you could argue that let's all buy an electric vehicle. Would that be a solution then for the world? Well, we don't think so, because it will solve only one problem, the emissions problem in the city, but the city will still be full of vehicles. So we think it's wise to combine buses, public transport, with bicycles, zero emission, of course, and the bicycles in separate lanes, of course, separated from the other traffic. Or we could combine bicycles with buses to go into the city. But okay, seriously, we want to reach the inner cities by bus. There may be good reasons why you cannot use your bicycle. So how to get into the inner city by bus? Well, this is a typical Dutch picture. Lots of bicycles and difficult roads for buses. So we said, let's do something in this area. An inspiration of me is the mayor of Bogota, Mr. Enrique Peñalosa, who said, an advanced city is not one where even the poor use cars, but rather one where even the rich use public transport or bicycles. So we decided to be part of this. We took a decision in 2017, 3 years ago, to be part in this segment, and invest a lot of money and a lot of time and energy in developing a modular bus, Movitas, which we will introduce to you now. This is a bus that is developed from scratch with a white sheet of paper, with a lot of enthusiastic engineers who have a vision, who have an idea to do it right from the start. So this bus, it will be modular, different lengths, different door positions, modular batteries, modular charging capacities. It will have lengths of 8.20 to 9.7 meters, a width of 2.5, height of 3 meters. So it is really into the niche segment of midi buses. Normal city bus is 12 meters. This one is just below it. So different door widths are possible, single plug or double plug. The front and the rear of the bus will always be the same. And we chose to use European components because they are known and reliable. You get good after-sales service. And of course, the bus is made in the Netherlands. The bus, it was designed as a modular bus from day one, meaning a little bit Tesla style. The batteries could be in the floor integrated, in the rear or in the roof if necessary. This creates a low center of gravity, and multiple battery packs are possible. It depends entirely on the operator's wishes. Of course, we are ready for depot charging or opportunity charging by induction or by pantograph. And of course, if you design a bus, you can have an optimal weight distribution. Very important for us was the layout of the bus. We wanted to have a complete low floor bus with a lot of freedom for the operator to have his own design of the interior and create a lot of space, a lot of air. So we wanted no wheelchair arches in the interior, which you see in a normal short wheelbase 12-meter bus. We created the opposite, a long wheelbase bus without obstruction from the wheel arches. Door positions can be flexible. You can see we can even create an airport bus with doors on both sides. And this gives you the freedom to choose your own layout. Lightweight is something that also comes to mind. Energy consumption is very important, especially for electric buses. So to start with a low weight is essential. Then it helps if you can create your own chassis and have it extremely lightweight. So still we used stainless steel because we wanted 15 years of warranty on the chassis, at least 1 million kilometers. So it should be durable material. Yet a high gross vehicle weight of 17.5 tons, which creates plenty of room, plenty of extra weight for batteries and passengers. And in the end, it results in a very low consumption of the bus. The air suspension that we have, it is our own development. We were not happy with what was available on the market. So we decided to develop this by ourselves. We wanted air suspension, of course, it should be very reliable, stable in corners, comfortable at the same time, quick kneeling possibilities, level driving, which is obvious, low maintenance, and very important to mention, it should give the driver a feel of being in control more than any other bus has ever seen. So this will be a new development for the bus industry, really. If you want to go into the inner city, you need a very small turning circle. The old European cities, they are not designed for 12-meter buses. They will not change, so we have to change the buses the way we build them. And we introduced rear wheel steering. This is new in the bus industry. This rear wheel steering, it is progressive steering. So in tight corners, it will steer more progressively than if you go straight. The steering angle can be adjusted. Of course, we have torque vectoring in the driveline. Single tires in the rear. So this should all result into less wear of tires and also less damage of tires, which is now common with the 12-meter buses and non-steered rear wheels. And of course, this gives you the possibility to use a crab modus. We had an excellent designer working for us who made a beautiful design of the bus. We are now nominated for the GIO, which is a design award in the Netherlands. By the end of this week, we will hear if we are winning this design award or not. But the fact that we are nominated is also nice to have. Important is you see in this drone picture, you see solar panels. We are also working with a supplier in the Netherlands for using solar panels, because it can also create extra energy for the low voltage batteries. It's part of the sustainability that we want. Thermal management, very important for electric buses. You might know that almost 50% of the energy can go to the thermal management on days with extreme temperatures, be it very warm or be it very cold. So we invested a lot of time and energy in creating a good environment for the passengers. So meaning tailor-made thermal management, where we reuse the driveline warmth for heating of the bus. We will heat up using an electric heat pump with a high efficiency. Of course, also the heating is completely zero emission. We don't use diesel-powered heaters. I don't believe in that. Of course, it is compliant to VDV standards. This is the German standard, where they use a temperature delta standard to evaluate electric buses. We've tested this in a climate chamber, learned a lot from it, and still improving the thermal management. Of course, it is connected. That means it is predictive maintenance ready. You can read a lot of data from a distance from the system. Double glazing for the passengers, meaning excellent isolation for heat or cold. And we have heated side windows for the driver cabin, as well as heated front screen. So the driver always has clear vision, even in extreme cold temperatures. Of course, preconditioning is nowadays standard. So the bus, when it is connected, charged during the night, it will be preconditioned, not only the batteries, but also the temperatures. So the bus is ready for a new day, completely warmed or cooled, depending on the time of the year. Which brings me to remote monitoring. Very important in the serviceability of bus is that you can see from a distance on a dashboard how the bus is functioning, how it is, what is the state of health. So that means the operator and Tribus will have real-time access to consumption of the bus, state of charge, remaining range, GPS data of the bus, speed and recuperation percentage, heating and cooling of the bus, temperatures of most of the components. This data will be logged, of course, and all in all, this means we are ready for predictive maintenance. So we can predict if we have enough data, we can predict the future maintenance and be ready well, before a failure happens. Because in the end, we want a bus that is very reliable with a maximum uptime, meaning you should be able to read the wear of the components and avoid unexpected downtime. We work with this with Vericity. This is a market leader in remote monitoring of buses. Then the driver cabin. This is very important. The driver is for us a very important person. This is his working space, so the climatization should be excellent. The visibility should be good. All in all, the driver has to work in this for 8 hours or more. So it should be a good environment, and we are compliant with ISO and VDV standards. It can be closed off fully by a polycarbonate door. These days of Corona, also important, but in the past, you also wanted this if the driver was not feeling safe. Good views, and to help the driver, we have cameras in the front, the rear, and opposite of the doors, so he can see what is going on around the bus. Finally, we also have rear view cameras possibility instead of mirrors. You see these more and more these days. Is this bus for real? I think so. I will show you a short movie, introduction movie that we made. It's 1.5 minutes, so please bear with me. Is it? No, it's not playing. Sorry about it. You can find it on our website, www.movitas.nl, or it's also on YouTube and Vimeo. So I don't know why it's not playing. Anyway, the bus is for real. We've shown it last year on Busworld. We'll be in VDV Elekbu in Berlin next year, and we will take the bus to the streets in 2021. And if you want to know more about it, of course, you can ask me. Is this bus future-proof? We think so. We are ready for fuel cell technology. The Movitas is also prepared for autonomous driving. Starting platooning is a first step. Autonomous driving will be still a few years away from us. But we think the Movitas will be fitting into the public transport in most cities, because we think the future of transport will be cashless. It will be driverless. It will be noiseless, easy with electric buses, seamless, and emissionless. Finally, it will also be very easy and problemless. meaning by using apps and so on, you can find your way in any city in the world. And it will be in a very high frequency. So we think a minibus will be the excellent answer for this in a high frequent inner city line. The Movitas will be a good partner for most operators. So this concludes my webinar. I would like to thank you very much for your attention and await for your questions. Thank you.
Thank you, Erik. There are already a couple of questions. A question related to charging time and range of the bus.
Mm-hmm.
So basically, what's the charging time like, and what's the range?
Well, basically, it depends on what the operator wants. We can have depot charging, overnight charging, also called slow charging. In that situation, you have a huge battery pack sufficient for 1 day of driving. So imagine something between 200 and 350 kilowatt hours, which should be charged then at night. That can be in a relatively slow power, like 50 kilowatts per hour. Alternatively, you can have opportunity charging, quick charging by pantograph. And there, well, I would like to say the sky is the limit, but nowadays pantographs have like 600 kilowatt power. So it depends on the available technique, and we are ready to implement it on the bus.
Thank you. Then there's another question. What is the planned size of the wheel rim?
The size of the wheel rim, the wheels are 22.5 inch. Is that?
Yeah, I guess that's what was asked.
Uh-huh.
And another question: when will the bus be ready for the road?
It will be ready for the road by March next year. We will have two prototypes driving then. We can use one of those prototypes for demonstrations. So if there's a city interested, we can take it there and let it drive in the city to verify the demands of the client.
Okay, then next question about heating the passenger compartment. What technology is used for that? And I believe you said that it's heated by heat pumps.
Yes, correct. So it is a heat pump system. We use it from a company called HEVAC in the Netherlands, who are experienced with this system and who are in a very advanced with this combination of reusing heat and cleverly distributing the warmth or the cold into the bus. So we are working very closely with them to develop this system.
Okay. Another question. What is the constructional maximum speed for the bus? If 80 kilometers per hour or over, can it be ordered with seat belts?
The maximum speed is technically 90 kilometers per hour. It can be ordered with seat belts, but it is really a class 1 bus. So that is something to keep in mind.
Okay. And then there is one more question. Is vehicle to grid charging something you might implement in the future? Why or why not?
The quick charging, the opportunity charging.
Oh, vehicle to grid charging, so two-way charging. So,
well,
so that means using the bus battery to feed to the grid as well.
Ah, okay. So bidirectional. So,
yeah.
Yeah, that is possible. Yeah.
Okay, then there's a couple of more specific questions about the range you already answered. Sort 2 consumption and maximum passenger capacity.
Yeah, passenger capacity is important. I haven't mentioned that before, but despite that we are in the MIDI segment, the capacity is still very big. You can think of like 55 passengers for the smallest one to 75 passengers for the largest Movitas. It depends, of course, also what the customer wants, how many seats they want, how many standing passengers. But in that range, we are going to build the bus.
And what kind of range you can offer for the bus?
Well, the range, like I said, it depends on what they want. Normally they would like overnight charging, so slow charging, and then you can think of ranges between 200 and 350 kilometers.
Thank you. Then, who is the supplier of the bus chassis?
This is our own development. We are working now with a supplier to build and to weld this chassis for us. But this is our own development.
Okay, then one more question about the energy use. What kind of percentage of the energy use could be covered by the solar panels?
Very little. Let's say the efficiency of solar panels is not so not by far not good enough for driving a bus. So we are using it to power the 24-volt batteries. Also, you cannot rely on solar panels. Or you can rely on them, but sometimes it is you are driving in the dark or in the shadows. So you should calculate the energy consumption of the bus without the solar panels. So it is very nice to have. We are doing this because we made a calculation that after 8 or 9 years of use in the Netherlands, you have your return on investment of it. Plus, it is a nice marketing tool to use. Second reason for using solar panels is more southern countries around the Mediterranean. They have a lot more solar hours than we have, and in those situations, it is an extra nice benefit to have. So we want to learn from it.
Thank you. Thank you, Erik.
Okay, you're welcome.
The second presentation will be slightly different style. We have a bit more technical, going a bit more deep technically inside of the charging process for the electrical buses. And I will present a project that we have run in Turku University of Applied Science during the last years. And then I will focus on the impact of the charging station on the lower voltage distribution grid with different interferences or impact that we can consider, look at what we have measured on charging stations, and then we can open a short discussion about that. I will focus on the opportunity charging in this presentation and on the low voltage distribution grid. Maybe a short introduction about myself. I work in the University of Applied Science in Turku on part-time, and University of Applied Science Western Switzerland also part-time. My focus for research is integration of renewable energy to the grid, with focus on power quality, electromagnetic compatibility, and different protection issues. We have developed in both university low voltage DC microgrid technology, in Switzerland with a pilot site, full scale, and in Turku with the SEBNet project so far. The control of this smart grid and this application when there is storage included is very important nowadays. Another aspect also, of course, is teaching all these activities, to share this knowledge with students. Very shortly about Turku University of Applied Science, the new laboratory for new energy research. We will focus on many things. There is PV, there is storage, but one aspect is to work on the converters and to see how the converters interfere or work together, cope with the grid when it's about converting energy. So we have a fast prototyping system, we have a grid simulator, and we have also acquired real-time targets. So we will connect these three systems together so that we are able to realize power hardware in the loop simulations where we can test different converters and test in different applications where the environment is simulated by the grid simulator, for instance. Now about this presentation and project, I think I don't have to repeat too much about the interest and the growing interest and the motivation to have more electrical buses around. Now, if we consider charging them, what are the possible impact on the grid? The power is usually pretty high, so we might have voltage instabilities. And coming together with it, overloads on the distribution network lines, transformers, and so on, which could require then oversizing of the grid or special developments for this charging infrastructure. On the user, if you have user close to the charging station, due to the variation of the power, we might have flicker, which means a fluctuation of the voltage that can be seen on the lighting. More important and more deep in the process is the non-linearity of those converters that are used for the charger. They generate harmonics, so oscillation at frequency that are multiple of the fundamental, and different interferences with different systems. If the level of harmonics goes very much up, we might enter in converter instabilities, and these converter instabilities can result in stopping the charging process or damaging part of the electrical system. So first on the project that we run about that is the SEBNet project for studying the charging load, the impact on power grid and power generation all together, and to study this in a simulated way. And another aspect was to build up a scaled down power hardware in the loop facility to modelize the hybrid charging with PV, storage, and so on, and to make be able to develop measurements, monitoring, and programming. in order to include the other aspect, for instance, the IoT, the cloud service, and so on, to control the charging station. I will come further on that. So we had the chance to be able to work on the new E-Fully line, which is a pilot site, connecting both the airport to the harbor of the city of Turku in southwest Finland. Project was realized by ordering 6 electrical buses, and both the buses are driving a route of over 13 kilometers. Talking about the charging or the bus technology first, it's a full electrical bus manufactured by Linker in Finland. And it was one of the first pantograph charger coming down from up the bus in Finland. The battery size of the bus is surprisingly small, 55 kilowatt hour for such a bus, comparing to a modern and fast electrical car, it's a smaller battery. So we need for that charging at each end of the line. There are 2 charging stations. This is a picture in the airport charging station, which has a power of 300 kilowatt and is able to charge this 55 kilowatt hour battery. Of course, not full, but from the state of charge, it arrives to the station in less than 4 minutes actually. So it's a Dutch company who has delivered this charging station, and it was commissioned by and installed by Turku Energia. And what is maybe important on the picture here is that you can see on the left the transformer station for the airport and the new transformer station and the charging infrastructure on the converter side beside it. Of course, there is a complementary bus depot charging with fast charger, which are 50 kilowatt. So the bus can be charged overnight in about 6 hours. Now we have measured, talking about the impact on the grid, we have measured these charging cycles. And you can see here that there are charging cycle about each 15 minutes, 20 minutes, and the charging cycle lasts for less than 4 minutes. And the first thing that we have seen is that there is an impact, of course, on the low voltage. Sorry, there is a mistake here. It's 0.7%, so it's below 1% the voltage drop, a few volts, which is, of course, not a problem. But we are connecting directly to the transformer station less than 10 meters away. So the idea of the project was to evaluate the case where the transformer station is not so close to the charging infrastructure if there is a remote location. A process for the research was to first evaluate what model we can use, how we can model the grid, and how we can check this voltage variation along the lines. So with the help of Turku Energia, we created a complete model of the distribution grid in the power flow simulation software. And you can see here, the airport station is quite much at the end of the line, but it's deserving, the network is deserving a lot of important charges. There, it's in industrial area, and this is most of it medium voltage to upper medium voltage. So we have 10 kilovolt to 20 kilovolt for most of this grid segmentation. So we implemented in details the complete distribution model in the software, simulation software for load flow. And we implemented, that was the difficult part of it, it was to find what kind of loads we have, what kind of profiles we have on different users. Actually, it does not impact too much. The grid is very well dimensioned. So we got in per unit extremely low voltage drops in the order of few volts, which was about what we expected in the simulation. So the voltage drop in the simulation corresponds very well to the measurements. Below 1%, as said before. And we can then use this modeling. We can use our method to check what happens in more remote location. So Turku is located close to the sea. We have several islands which are part of the city, and one of them is Ruissalo. It's a pretty long island, and the road from the center is roughly 8 kilometers. So you can imagine to deserve this island with very low energy consumptions, only few houses. The line is much less robust. And we have here the grid that deserves this island. It's supplied through underwater cable. So we have again make a complete model in the simulation software in order to check what would happen at the end of the line. And maybe one more specialty, it's a bit difficult to see here at the end of the line, but the bus station, the bus stop is a bit more remote than the transformer station. So we expect much more variation. So if the bus would be charged at the same position where it's stopping now compared to the transformer station, then we see 8% voltage drop, which is very close to what the standard accepts. Maximal voltage drop would be 10%. And this is considering that there is no other interferences. So a much more tricky situation for this remote location. The idea would be to create a hub where we can add energy and we can add some battery. If we store part of the energy, then we can make the cycles for the power to charge the bus much more smaller energy or power, and we could then reduce the voltage variations. So with a good storage, we were able, for instance, to run a simulation where we would get only 1.5% voltage drop. And it's not a very big battery that is needed. For instance, below 10, 15 kilowatt hour would be enough for that. So what is the concept? The concept is to store energy in the local buffer during the time there is no bus, and reuse the stored energy and feed it to the bus when the bus is charging. Since the cycle for the charging is roughly 1/3 of the use of the peak and nothing for 2/3 of it, it's enough to size a battery that would be enough to fill the bus battery, or 2/3 of it would be already enough. Now, we don't need to have zero power. We want to have an averaged power that is roughly around 100 kilowatt. So it means we can even reduce the battery significantly. Our idea to prove the concept, where we have the bus charging station that is completed with PV energy production and a local storage. All these three elements are working with low voltage DC, in contrary to the distribution grid, which is in AC. So it makes sense to create a low voltage DC microgrid around this charging station. So we would save the number of conversion steps and get much more efficient and less having dropping the costs. So we have made a simulation of this system, not only in software. We have made a downscale hardware in the loop simulator in the Turku University of Applied Science. You can see here these simulators, and we were lucky enough to find enough information about the real charging station, so we could use very similar converters that are used for the real charging station. We connected around that the battery and the different simulators, one for the photovoltaic supply and one for the bus charging, fast eBussed battery charger. In fact, this is not the relevant part of this presentation, the results about the simulator, but it's functional. And in between, we have seen that some suppliers come with this very similar solution on their product range, where we have a buffer for this fast charging and even included PV photovoltaic production. And it's all about cycle life of the battery and size of the battery. We think that if you have this charging on the route, you need a smaller battery inside of the bus, and we can buffer on the ground with a less expensive battery. They are not needed to be transported. They can have different characteristics, and as I presented, can be pretty small. The last section of my presentation is about power quality. So for the ones who are not used to this concept, I try to make it simple. When you connect converters to the grid, they generate different disturbances. And there are standards that are checking these values over the time. So we can measure over 1 day, for instance, and that make a lot of statistics about different parameters. For instance, the variation of the voltage, harmonics, flicker, and so on. And in the bus charging station, everything looks pretty good. You can see here a summarize of those measurements, and you can see that the limit is never really reached. If we consider in red the 90% of the time, which is according to the rules, the requirement. But we can see harmonics, it means oscillations on the grid that occur part of the time, maybe 5%, but are going over the limits. So we wanted to analyze this a bit. This is the other charging stations about similar situation, only problems with the oscillations. So we are able to analyze those oscillations at different frequencies. Here you can see multiple of the fundamental. And what we can see very rapidly is that we have some resonance in order of 1,200 to 1,300 Hertz, which is normally not occurring. And the resonance is normally okay, but in some time goes clearly over the limits. We can see that if we go further in the frequency, this is higher frequency. This is between 2 and 10 kilohertz, where there is very little regulation for the moment. There is, but it's not so problematic. Here you can see the normal oscillation due to the switching frequency of the converter. So this is really good in that aspect. This is a normal ramp up. So we were trying to figure out where this oscillation come from. So we have checked the ramp up in normal case. You can see the current going from 0 up to the rated current in few seconds. Now, when we look on the time and we look on the voltage, the power, a bit more detailed on time, we can see those cycles, the normal charging cycles, a bit like before. The impact on the supply voltage, of course, there is this 2 volts voltage trip, very normal. But what we can see is that there are kind of false starts where nothing happened or just variation in a moment. And just during this false start, there we see exactly our oscillations at 1,200 to 1,300 Hertz, and the value of the current is pretty high. So this is not a normal behavior. Looking in time, how this happens, I have looked in Zoom of one of those false starts, and here we can see that the current does not go up like normally. It just stays on undefined level for a couple of seconds, 10 seconds, we don't know exactly. Zooming this area when the problem starts, we can see here a lot of disturbances, a lot of oscillations. This is really not a really normal behavior, or let's say not optimal. So I zoom a bit deeper, and there we can see this oscillation. And indeed, the current with very high values, the order of 50 amp, is oscillating by more than 1 kilohertz. So there is a very unstable behavior at this point. What does that mean? And where does it come from? It's not completely abnormal, but it's problematic if it does not get under control. To feed the bus with the exact voltage and current, we need a converter. It's working with switching mode. And you can see here the converter controllers. And those controllers try to keep the things very smooth and very steady and just according to the demand of the battery. Now, there can be a lot of factors that can make this controller unstable. I have listed them here. And the most important factors that we can have is how far is the bus charging installation from the bus, or from the transformer station actually. How many converters are connected in parallel? Are the harmonics already present to the grid so that the controller would react? Of course, there is the synchronization of the grid that can go wrong. There are many things in the controller, in the switch mode, and so on. What we think is that we have a resonance, and this is already treated in many examples of EV charging. For instance, EDF had made a quite strong, important study about instability of their EV chargers for small cars. And you can see here, this phenomena is resembling what we are measuring on the battery, on the bus charging station. So, time to the conclusions. What I want to say with this example is that if you test the converter alone, everything is probably fine. When you connect it to the grid, it can have good behavior, but it can have not very stable behavior, which is very often the case. If the controller managed to get back on track, like it seems to be the case after a few seconds and few trial, the controller gets back in track, then the customer is satisfied. In general, it's working fine. But the risk is that if you change the condition of this charging station and put this converter in other places, then you might be a bit more in trouble. There are other converters, there might be longer cables, and then the stability does not come back to its point. So this requirement on the charging station will influence a bit the choices, and that is, of course, an important aspect to be considered. The requirement at the end is that you must be close to a transformer, and this means that we have a bit more cost than just expected if we don't care about those behaviors. And that's an important part of the technical issues to fix here. So I hope this was according to the request of the organizer of the presentation. If you have questions, I'm pleased to listen to them.
Thank you, Dominique. That was a very interesting presentation with a lot of information. I think everyone has a lot to digest after that.
Sorry for that.
But there's a question about data. Are there outliers in the data, and at which point does data analytics come in?
Of course, these measurements on the data that do not come so easily on the data because it needs a very advanced power quality analyzer. But if you look at the charging process and the charging profile, maybe you can see and record the aspects that you have the false start of the charging, for instance. And if you have access to that information, then an inspection can be done and the problem can be maybe improved. Regarding the battery, the data is interesting to collect data from the bus regarding, for instance, the load, the state of the charge of the battery, so that you can control the charging station. This is the other aspect of my presentation here. If you have this system, if you have the data and you know what the state of the charge of the battery when it comes to the station, you can manage the energy a bit in different ways. For instance, charging the buffer battery more or less, giving the energy available for the users, or feeding simply the energy from the PV directly to the grid. So that was what we tried to develop in this project. Does it answer the question?
Yes, yes. Thank you. And there's a question about depot charging, if it was considered that it could have been up to 80 kilowatts. I don't know if you know anything about that.
Yeah, I took exactly this picture here on purpose. We have in the literature, in the measurements, there is a clear knowledge that when you multiply the number of converters, you have to take some measures about stability of converters. If all the charges come from same suppliers, the risk can be reduced. They have their models and they have their very good advanced knowledge how to develop a converter and a controller. But if you start to mix up with different converters, for instance, here I see PV production on the roof and those converter, they might come quite interesting surprises. And of course, we will solve these problems. I don't say that I don't want to break the development of these, but we will go faster if we take good measure and if we take good care of those different aspects. Because if one converter starts to get really unstable, the voltage will reach over the limits in these oscillations and the protection will trip out. And then the whole station is stopped for a moment. And that's what happened in a train station in Paris a couple of years ago, when they started to put converters in the train and the converter started to be unstable. The voltage on the catenary went too high and the whole station was shut down for quite a while. And this is what we want to avoid. So, of course, this voltage in variation of voltage also, if you charge many bus with a lot of power, you will need to have a very strong medium voltage transformer station and or several of them, for instance. That would be a good solution, but there will be costs that are coming maybe a bit like a surprise if you don't consider that. So we have a bit the same requirement. Is it distributed or on the routes charging, opportunity charging, or then if we have a lot of converters all together? At the end, the problem is a bit the same.
Thank you, Dominique. Then there is a question about the battery capacity. If it would be higher, like 200 kilowatt hours, for example, how would it affect the buffer capacity needed in the charging stations?
Yeah, of course, if you multiply the size of the battery by factor 4 and you use that, so the route will be longer, and it means that you need to recharge with more energy. You multiply the problem by the same equation on the same factor on the buffer that you need on the end of the line. So if you have larger battery in the bus, you have a larger buffer. but still the ratio between the bus battery and the buffer battery is maybe factor 3, smaller. And as I said, the technology can be really different. You don't need to have a transportable battery, and that's a very important advantage.
Thank you. Thank you, Dominique. That was all the questions right now, and we have spent the time reserved for this session today. So I'd like to thank you, Dominique and Erik, for your presentations, and I'd like to thank all the participants as well. And the presentations will be shared on the project website, so you have the opportunity to go back and go back to the presentations, and I'm sure that both Dominique and Erik are happy to answer your questions afterwards by email too. So
yes, of course.
On behalf of eBussed, I'd like to thank everyone and wish you a nice day.
Thank you.
And thanks from me to